This clip shows a tennis ball at rest before being dropped off the ledge of a treehouse. The height of the treehouse is approximately 3.7 meters. By taking a particular height that the tennis ball was at during the fall, and the corresponding time it took to get to that height, we were able to find the velocity. We repeated this process 4 times to find the accurate average velocities.
For example, at this point the tennis ball has traveled 1.1 meters in 0.4 seconds. Therefore, we know that the velocity at this instant in time is about 2.7 meters per second. However, since this tennis ball is classified as a projectile, we know that the velocity will have increased by the time it hits the ground.
In the position versus time graph shown, the blue line represents the data collected and the decreasing nonlinear trend. The orange line also shows a decreasing linear trend, but instead it represents the average velocity of the trip.
In the velocity versus time graph, the blue line shows an upward linear trend representing the average change in velocity for the trip.
Because the velocity was increasing at a constant rate, there was no change in acceleration.
To find the acceleration of the tennis ball, we found the change in velocity, then divided that by the total time.
Because the tennis ball is a projectile, this number should have been close to 9.8 because of the rate of acceleration due to gravity. However, our acceleration was significantly less than 9.8 due to air resistance and friction. The acceleration that we calculated was about 4 meters per second squared, shown by the orange linear line on our graph. The blue linear line on our graph shows the average acceleration due to gravity, 9.8 meters per second squared.
Next, we found the potential and kinetic energy of the tennis ball during its journey. When the tennis ball was at rest, there was no kinetic energy, inversely causing the potential energy to reach its peak at approximately 2.2 joules.
The tennis ball drops and the potential energy decreases as it nears the ground. Due to the law of conservation of energy, this means that the kinetic energy increases.
And finally, right before the ball hits the ground, the potential energy reaches its lowest at 0 joules. In turn, the kinetic energy has now reached its highest. Due to the law of conservation of energy, we know that at this point the kinetic energy will be 2.2 joules.
As demonstrated by the graphs, the total amount of energy during the fall stays constant.
The first of Newton's laws explains that an object at rest will stay at rest unless acted upon by an unbalanced force. When the tennis ball was at rest, it remained at rest until Chloe dropped it and it was set in motion. The ball also stayed in motion until it hit the ground.
Newton's second law explains that we can find the force of the tennis ball by multiplying the mass and acceleration together. The total mass is 0.05 kilograms, and we know that the acceleration is approximately 4 meters per second squared. By multiplying these variables together, we know that the total force is approximately 0.2 newtons.
Newton's third law states that when an object of a certain mass and acceleration exerts a force on another object, the second object pushes back with an equal force. This did not pertain to our experiment because our ball is classified as a projectile. This means that scientifically the only force acting upon the ball is gravity. However, in the real world, air resistance could be considered a minor force acting upon the object.